Nowadays, any willing individuals can deploy their own Ethereum, Hyperledger Fabric, and many other blockchain networks. However, designing and deploying the right network for a project is still a challenging task for architects. The challenge is further exacerbated by the ambiguity in concepts that we use around blockchain network. Hi, my name is Nguyen from the University of Adelaide, and today, in this presentation, we will present our research on anatomy, concept, and design space of blockchain network. First, let's talk about motivation. According to a recent census by the Australian government, if you are an Australian, there's an 85% chance that you live by the coast. Otherwise, it is likely that you would head to the shores for holiday. In fact, beaches of Australia welcome 100 million visitors every year. Protecting more than 100 million visitors every year is challenging. In fact, last year, Surf Life Saving Australia conducted more than 10,000 rescues. To achieve this level of performance, effective coordination is necessary. And such a coordination only happens when we have superior information and awareness about the situation and the environment. In December 2019, Surf Life Saving South Australia and Defence Science and Technology Group conducted a joint exercise on information superiority. Our research team participated to answer a question: how to build a decentralized, trustless, and resilient platform for integrating an IoT infrastructure with a command and control center. Early on in this project, we decided that the backbone of our platform would be a blockchain network. Therefore, the design and deployment of blockchain network became our focus. Over the course of this project, we came across several problems. The first one is about communicating blockchain concepts to stakeholders and developers. So in blockchain space, there are too many concepts, and often there's a certain degree of ambiguity. For example, when we talk about blockchain, are we talking about the network, the data structure, or the whole system? When we talk about blockchain developers, are we talking about the one who builds smart contract? Or are we talking about the one who develop protocols? The second problem is that there's a lack of a design space for a blockchain network so that we can know our options, we can know the degree of freedom that we have when we design, so that we have a way to describe our design to other stakeholders. To solve the communication problem, we created a concept map which shows concepts of blockchain that are relevant to software engineering and the relations among those concepts. To solve the second problem, we propose a design space, which is essentially a multi-dimensional space which captures decisions and options that are available to architects when they design and deploy a new blockchain network. Next, we will discuss the research method that we used to develop the design space and the concept map. We organized the design space into two groups. The protocol decisions capture the variations in terms of design and implementation of different components of a blockchain protocol. The network deployment decision capture different decisions and options that we have when we actually deploy a blockchain network on an infrastructure. To identify protocol decision, we analyze academic sources on software architecture for blockchain and also technical papers of Bitcoin, Ethereum, Corda, Quorum, Fabric, most popular blockchain networks. Based on these sources, we extract modules, workflow, and physical structure of a blockchain network and compile them into blockchain network anatomy. The modules that are available in this anatomy becomes the design decisions, and the options to design and implement those modules becomes the design options. To identify network deployment decisions, we start from documents and tutorials from popular blockchain networks. From these documents, we extract the process, and for each step, we extract the decisions that we can have when we deploy the network. Compiling these decisions together, they become the network deployment decisions of the design space. We also rely on academic sources and technical paper to extract concepts and relations so that we can compile the concept map. Now that we have discussed the research method, let's look at the concept map of blockchain. A blockchain network is a peer-to-peer network consisting of multiple blockchain nodes. These nodes can be organized into three types: full node, lightweight node, and remote node. To participate in the blockchain network, a blockchain node needs to run a blockchain client, such as Go Ethereum. This client implements a certain blockchain protocol, such as Ethereum. When we package the blockchain client with some utilities for development and operation of a blockchain network, and we have a blockchain platform. Now let's go back to the protocol. The purpose of a protocol is to maintain and update a blockchain data structure. This data structure hosts a ledger and the smart contract. A distributed application is an application that uses the ledger and the smart contract as the backend. So, blockchain application developers work with smart contract and distributed applications. Blockchain developers work with client, protocols, and blockchain platforms. Blockchain network developers work with facilities, infrastructure to run and operate and maintain blockchain network. So as you can see, we don't have the generic term of blockchain in this concept map. Next, let's discuss the anatomy of a blockchain network so that we can clarify some of the concepts that we just discussed in the concept map. Lying at the heart of most blockchain protocols is a state machine with accept transaction to move the blockchain between different states. Because this state machine needs to be replicated across a wide range of blockchain nodes, usually it runs inside a virtual machine such as EVM, JVM. In some cases, it's run in Docker containers. So the transaction to operate this state machine comes from a software called wallet, which is used by clients to sign transactions. So the transaction would come to a validator where the invalid transaction would be removed. The definition of the invalid transaction depends on different blockchain protocol, as we will see. Next, the consensus component will order the validated transaction so that the order of transaction would go to different nodes in the same order. These components, validator, consensus, state machine, they becomes the heart of a blockchain protocol. And the blockchain protocol runs on full node, as we mentioned. But not every participant in the blockchain needs to have the capabilities and the burden of a full node. So we have lightweight nodes, which just keep the header of the blockchain so that they can validate transaction to a certain degree, but they need to rely on a full node that they trust. To interact with the network, we also have network interface component, and then the remote nodes usually will interact with the full node via the network interface. Many blockchains that we use in enterprise application involve some extension, such as identity management, authentication and authorization, and privacy preserving components. So the way we implement these components becomes different design decisions and options that we have in the design space. Now that we have discussed the anatomy and the concept map of blockchain, let's talk about the design space. We further organize the protocol decisions into subgroups. The first subgroup is about state machine. Decisions in this group control different aspects of a state machine of the blockchain protocol, such as the model of the state, the model of contract, how we're going to use virtual machine, how are we going to implement the validator? The second group is about consensus. Decisions in this group is important because they have a lot of implication on how the network perform and behave. On one end of the spectrum, we have Byzantine fault-tolerant and cyber-tolerant protocol, such as Nakamoto consensus, using proof of work. On the other side of the spectrum, we have crash-tolerant protocol. The last group of protocol decision is about enterprise extensions. For example, how we're going to model the identity of participants, how are we going to authenticate and authorize participants, how are we going to preserve participants' privacy. For example, are we going to use multiple blockchain database on one network, or are we going to break the network into multiple subnets for different participants? Usually, application developers and network developers don't make a lot of decisions about a protocol except the consensus. However, it is still good to know and understand these decisions because it would help them to analyze and compare different blockchain networks and protocols that they're going to use in their project. We also organize network decisions into subgroups. The first subgroup is about full node. These decisions are among the most important decisions that we can make when we design and deploy a blockchain network, because full node runs the network. So the first decision is about mapping between full node and participant. Would it be one-to-one, one-to-many, many-to-one, or shall we open the network to the public so that anyone can become a full node? Next decision is about full node deployment. Would they be in the same cloud, multiple clouds, or maybe can we run them on network computer or Raspberry Pi? The next decision is about the distribution of mining power. This decision will control the governance and the security of the network. So shall all participants take part in the mining process? Would it be only one participant performing the mining service for all the participants? Would it be M out of N, or shall we open these decisions to participants? The next subgroup is about lightweight nodes. So different from full node, decision about lightweight node is not as structured. It depends more on the project. So for some projects, we wouldn't need to use any lightweight nodes. The next group of decision is about remote nodes. That means the nodes that the clients use to interact with the blockchain network. So we also have to make decision about mapping between remote nodes and participants. And we also have to decide how we're going to deploy those remote nodes, whether they are going to be standalone application, or we're going to embed it into another application that clients has been using to interact with the system. The next group of decision is about the network interface. So we have to decide on interface type and interface deployment. Are we going to deploy the interface on as a standalone service on a cloud maybe? Or are we going to embed it in a full node? Or are we going to embed it in a lightweight node that we deployed previously? Finally, the last group of decision is about node communication. In this group, we will decide on how peers nodes are going to communicate with each other and how they're going to discover each other. So together, these decisions are options that are available for architects when they design and deploy a blockchain network. Now that we have discussed concept, anatomy, and design space of blockchain network, let's see how these tools can be applied to a real project. For this case study, we will use the platform that we mentioned in the beginning. The idea of this platform is to interface different portable ad hoc IoT infrastructure with a command and control center. So each of these infrastructure, as can be seen on the screen, consists of multiple Bluetooth low power sensors. Because these sensors are limited in terms of capabilities and functionality, they have to send their data back to gateway device, which in turn would send forward the data around the network and do additional processing. An ad hoc IoT infrastructure can also include more powerful computing node called aggregator, which has more processing capabilities so that we can do more edge computing. The back end of our platform is a blockchain network that is going to run directly on the portable IoT infrastructure. So this network has 4 requirements. The first requirement is that it needs to support smart contract because we need to store data and also we need to perform some arbitrary computational task. Second, it needs to ensure the independence of the nodes. That means the disconnected nodes can still append data to the blockchain. Third, it needs to be efficient. In other words, it needs to minimize CPU time and memory consumptions because we're using some low power, even battery power computing device. And finally, the blockchain clients needs to be highly portable because it's going to operate on different instruction set architectures like ARM and x64. Our first decision when designing this network is about its participants. Would it be the whole infrastructure as one participant? Would every sensor a participant? Or would every node a participant? This decision is important because it determines the governance and participation in the network. So we realize that infrastructure as one participant is trivial to implement, but at the same time it's too broad and it doesn't provide us much value. Essentially, if infrastructure as a participant, then there would be only one node, perhaps running on aggregator, and then we wouldn't be able to achieve independence, we wouldn't be able to achieve all the quality that we expect when we deploy the blockchain network. On the other hand, sensor as participants is too fine-grained because the sensor by themselves are not able to run the network. So the network would be running elsewhere. It would just make the network more complex. So in the end, we decided to turn every node as a participant. So that means the aggregator and gateway, each one of them would have their own public key, private key, participate as a participant in this network. The remaining of design decisions based on the requirements are as follows. So first, we need to support smart contract. So because of these requirements, several blockchain protocols candidates were removed from the list, including Bitcoin and IOTA. Second, we need to have portability. That means that the blockchain protocol needs to be able to run with reasonable performance on ARM infrastructure. So after an analysis, we found that Hyperledger Fabric and Ethereum has some support to run on Raspberry Pi. However, after an initial performance study, we realized that Hyperledger Fabric runs too slow on Raspberry Pi. So we decided to go with Ethereum. Next, we need to ensure that the network is efficient enough to run on low power device like Raspberry Pi. So because of this limitation, we cannot run proof of work protocol because it's simply too heavy. So we decided to go with proof of authority. Finally, we need to ensure that the network can allow the participants to operate even though they are disconnected from their peers for a certain amount of time. So for this decision, we decided that we cannot use any lightweight node because lightweight node does not contain every information, every smart contract that a node needs to do its job. So because of that, we decided to distribute the full node on every participant. That means every Raspberry Pi, every aggregator node in the system have one full Ethereum node running proof of work. And for the remote node, that means the application that the system used to put the data to the blockchain. We decided that every participant would have one version of their remote node, and that would be embedded into the application that are already there to interact with the IoT sensor. And for the network interface, we decided to use both RPC and IPC API And we embedded this interface directly into the Ethereum full node instead of running a separate service. And for communication, we just use the default configuration of Ethereum using gossip-based protocol. But we switched to using static peer list instead of using dynamic node discovery. This is the final design of the system after we apply those design decisions. The green part of the architecture represents the IoT pipeline, where the gateway collects the sensor data from Bluetooth sensor and send it back to an IoT middleware. The red part represents the blockchain part of the system. In summary, the ambiguity in blockchain concepts that prevent clear communications and the lack of a design space for blockchain network are some problems facing architects when they try to design and deploy blockchain network. In this research, we propose a concept map and design space to solve this problem. For our future work, we aim to find a correlation between quality and the decisions of a network. We also aim to find a correlation between different decisions because, as you know, these decisions are not entirely independent from each other. We also aim to define a process so that we can guide architects through the design space in a systematic way. Finally, we aim to conduct an empirical evaluation of this method